You've probably seen an AI agent nail a complex task in a live demo, only to watch it completely forget what it did the moment the session ends. That's not a quirk. It's a fundamental architecture problem, and it's the single biggest reason AI agents fail in real-world production. Every AI agent runs on a context window, a fixed block of text it can actively hold in mind at one time. Think of it as the agent's working memory. The moment that window fills up, earlier information gets pushed out entirely. This creates a serious problem in long-running workflows. An agent that hit a dead end on step 4 might try the exact same dead end again on step 22, because it can no longer see what it did before. The solution isn't a bigger context window. It's a dedicated memory architecture that lives outside the context window entirely, a persistent store the agent actively reads from and writes to as it works. Modern agent memory systems break down into 4 distinct types: working memory, which is the context window itself; episodic memory, which records past interactions; semantic memory, which stores facts and world knowledge; and procedural memory, which encodes how to complete specific tasks. Episodic memory is the biggest leap forward. After finishing a task, the agent writes a structured record, what it attempted, what succeeded, what failed, to an external database. The next time a similar task begins, it retrieves that record before doing anything else. The most common storage technology for this is a vector database. The agent converts its memories into numerical embeddings, stores them, and later retrieves only the most relevant ones using similarity search, a smarter, meaning-aware version of keyword lookup. Retrieval is where the real engineering happens. The agent doesn't dump everything it has ever stored back into its context. That would defeat the purpose. Instead, it queries for only the most relevant memories, keeping the active context window clean and focused on the task at hand. Orchestration frameworks like LangGraph and MemGPT have built memory management directly into the agent loop. The agent itself decides when to write a memory, when to retrieve one, and when to compress old records to free up space for new information. Procedural memory takes this even further. Agents can store not just facts, but full reusable workflows, step-by-step plans for tasks they have already executed. Instead of reasoning from scratch every single time, the agent retrieves a proven playbook and adapts it. In multi-agent systems, memory becomes a shared resource. Multiple agents can read from and write to a common memory store, building on each other's work without passing enormous context payloads back and forth across the network. The practical results are measurable. Engineering teams deploying agents with persistent memory systems report fewer repeated errors and faster task completion, because the agent isn't relearning the same hard lessons at the start of every new session. But there's a real danger called memory poisoning. If an agent stores a bad memory, built on a wrong assumption or a hallucination, it carries that error into every future session. Robust architectures counter this with confidence scoring and human validation checkpoints for high-stakes writes. We're moving toward agents that maintain rich, evolving internal models of the environments they operate in, not just completing tasks, but genuinely improving at them over time. That's what separates a truly autonomous agent from a sophisticated autocomplete. If you want to understand every layer of how agentic AI systems are actually built, memory, planning, orchestration, and everything in between, subscribe and hit the bell. We break down real autonomous AI architecture, one system at a time.